Welcome. In this video, we are going to jump into section 2.6, which is talking about the second derivative and concavity. So let's take a look at some notation to start, and then we'll jump into a couple second derivative problems. So notation, there's going to be three kind of main notations that we'll use in this course for a second derivative, one using that f double prime notation, or the Lagrange notation. We have the y double prime in the second notation. That's also a second derivative of a y function. And then third, we have the Leibniz notation, which is our d notation, which says d squared y over dx squared would be the second derivative notation for our d notation. So all three of these are referring to the same operation of the second derivative. A lot of the time we'll be using that f double prime to work out the second derivative. So let's go ahead and jump into a couple second derivative problems. And we'll jump into part A, which is going to be f of x is equal to x cubed plus 2 to the fourth power. So if I want to take a second derivative, I first need to find the first derivative, and then we'll take a derivative of the first derivative to get the second. So it's a two-part process. So first, I'm going to go ahead and find my f prime of x. So we'll have f prime of x as our first derivative. It looks like this is going to be a chain rule problem for us. So let's go ahead and apply the chain rule. That would say the outer function here is that fourth power. So I'm going to bring the fourth power down, raise my function, x cubed plus 2, that stuff, to the 4 minus 1, which is 3. And then I need to multiply by the inner derivative, which is the derivative of this inner function, which is, in this case, 3x squared would be the inner derivative of x cubed plus 2. So taking the chain rule there, we have our first derivative f prime of x. So now, taking a look at f prime, we want to consider, well, how would I find f double prime? We'll just do that right underneath, f double prime of x. It looks like we have a product function now. If I split this up into two parts, this is one function of x, and we can list out a second function of x, which is the 3x squared. So let's go ahead and list out our product rule. I'm going to do the derivative of the first function. So I'll go back in blue. This will be the derivative of the first will be, again, another chain rule. So I'm going to bring down the 3. So that will be a 12 x cubed plus 2, now raised to the second power, times the derivative of the inner function, which again is going to be that same 3x squared. That's the derivative of the first. Then I'll list my second function, which is still 3x squared itself. And then we'll add the first function again. And then the derivative of the second, which is the derivative of 3x squared. So we'll do the derivative of 3x squared. We'll write that in red. That'll just be 6x with the power rule. So we can certainly simplify this if we'd like. Maybe a little bit of simplification might be nice here. If we take a look at the terms that we can combine with the product, we have 12, 3, and 3 again. That would be 9 times 12. So we could list that as 108. And then we'll have x to the fourth power. If I take each of those x to the squareds together, that's x to the fourth. And we'll do that x cubed plus 2 quantity squared. The second part we can simplify with the second term. That's going to be 4 and 6x give me 24x. And then we can list out our x to the third plus 2 to the third. And I think that's a pretty good place to leave it. That's an alright way to represent our second derivative. Let's go ahead and take a look at the g of x function. This is a natural log function. So let's consider the first derivative again. I think we'll need the chain rule again for the g prime of x function here. So we'll take g prime of x. Whenever we have a natural log function, the first part is going to be just 1 divided by the argument. So whatever the argument is. And then we want the derivative of the argument itself, or the inner function in this case. The inner function is what's sitting inside. That would just be the derivative of x squared plus 3x. And so that would be a 2x plus 3. So the product there, we could put really as a quotient now of 2x plus 3, and then just divide it by x squared plus 3x. So that's our first derivative. But we're not quite done. We want to find a g double prime, a second derivative function, which here we can now apply a quotient rule. So this is a quotient of two functions. So let's do g double prime, and we'll practice our quotient rule here for the second derivative. The first thing I'm going to do before I forget is let's go ahead and just write that denominator squared on the bottom. That's the denominator should be x squared plus 3x quantity squared. And then from there, we can start to list out our derivative combination in the numerator. So that would be first, write the denominator, x squared plus 3x, times the derivative of the numerator. The derivative of the numerator would just be 2, using the power rule. And then we'll subtract the derivative of the denominator, which is 2x plus 3, times, well, here we'll have the numerator again, which the numerator here is just going to be another 2x plus 3. So we could just do that quantity squared if we'd like, and might as well do a little bit of simplification there. We can maybe list this out. We could distribute this 2. We'll do that real quick to do 2x squared plus 6x. And then we could list out the other portion as just 2x plus 3. And that's quantity squared. All over the x squared plus 3x quantity squared. So that's an okay place to leave it. We have evaluated the second derivative. If we were to evaluate this at a single point on the domain of g, we might want to simplify it a little bit better, but that's pretty good for right now. So let's take a look at maybe a first application with the second derivative. What could be the second derivative be used for? The first derivative we can consider as of a position function can tell us the velocity of a point or a object at any one time. And the second derivative we can think of as a rate of change of that velocity, which we would call the acceleration. So this is maybe the first example of how the first and second derivative could be used, one as velocity and the second derivative as the acceleration of an object or particle. So let's consider this example with acceleration and velocity. So given the position function of a particle, s of t, that's the position function at any one time t, where the particle's position is measured in feet and t is measured in seconds, let's go ahead and find the following. We want to find what is the velocity function, v of t. So this is just the general velocity function at any one time t. We could find by, again, taking the derivative. So s prime of t, that position function, its derivative is going to be defined as v of t, the velocity function. So here we can just take a power rule for our s prime of t. This would be defined as, looks like 6t squared minus 40t, and then minus 1. And again, this would be measured as an output in, looks like our time is seconds and our measurement is feet. So this would be measured in feet per second if we would evaluate this. Feet per second as distance traveled over time. So that would give us the instantaneous speed or velocity at any one time for that particle. What is the acceleration function, a of t? So the a of t can be expressed in a couple ways. This could be expressed as the second derivative of the position, or in other words, we could say that's the derivative of our velocity, or the rate of change of our velocity that's mentioned up above here, the rate of change of our velocity. Again, all these are saying the acceleration. We call that a of t. So a derivative of the v function up above, we can do the power rule again. That would be 12t minus 40. And again, here, since this is the rate of change of our velocity, well, we would say this is going to be feet per second is the velocity, but we want rate of change of that. So we're wanting to see how the rate of change, f of x, feet per second, is changing over time. So this is how we would get feet per second. In other words, we would call that feet per second squared. So that's our units for our acceleration, feet per second squared. Because we're measuring how the speed here is changing over time. Part C asks us to be a little bit more specific at a point in time. What is the particle's velocity or speed after 2 seconds? So here we could say the velocity after 2 seconds could be defined as v evaluated at time equals 2. So here we're just going to evaluate our function, 6 times 2 squared minus 40 times 2 minus 1. So it looks like we'll have 24 minus 80 and minus 1. So I think if we evaluate that, we'll get a quantity of negative 55 feet per second. We evaluate that all the way down. And actually, we should get 57. Let's do that again. We'll have 56, negative 56, negative 57. That's correct. Negative 57. Let's get that right. Negative 57. There we go. And last but not least, we can take a look at the velocity or acceleration in part D. We want to figure out, will the particle be accelerating or decelerating after 3 seconds? So in other words, we're going to test the a of t function at 3 seconds. We can consider that portion there. We have 12 times t, which is now 3 seconds, minus 40. And so we'll have 36 minus 40, which is, in the end, looks like negative 4. That's going to be feet per second squared. And in this case, we would say this is a particle is decelerating at this moment in time because the acceleration is negative. So I would say that our particle is decelerating at 4 feet per second. In other words, its acceleration is negative 4 feet per second squared. So we would be decelerating at this moment in time. Let's consider the concept of concavity for a moment. This will be our look into the definition of what is concavity, how is it measured. So given a function f of x where f prime of x and f double prime exist, part A would say that f of x will have an inflection point, that's an important word for us, an inflection point, where f double prime of x is equal to 0. Inflection points are where our concavity changes from up to down. So let's maybe note that inflection point here, we'll call it just an IP, this is where the point at which our inflection or our concavity, and when we think of concavity, we want to think curvature. Changes. So the curvature of our function changes. Concave up function will be found where the second derivative is positive. So we will concave up when our second derivative is greater than 0, and concave down where our second derivative is negative. Another important piece that we'll want to consider is the idea of a critical point. So a critical point of a function down below, this definition tells us for a function f of x is a value, x equals a, some specific value, in the domain of f of x where either f prime of a is equal to 0 or f prime of a is undefined. So this tells us either our derivative is 0, in other words, we have a 0 tangent slope. So this would tell us that we have a 0 tangent slope. Or our tangent slope would be undefined. So to walk through this idea of concavity first, we'll take a look at this graph problem, and then we will take a look at what we would call the second derivative test with concavity. So we want to use the graph of f of x to answer the following questions. We have our graph here on the right, quadratic, or not a quadratic, but just a polynomial graph. Looks like maybe a 4th degree polynomial, but that doesn't matter necessarily for what we're doing. So let's consider part A first. We want to find what are the x values of the critical points of f of x. Again, we're going to want to consider again, where do we have a 0 tangent slope on this graph? Well, let's go ahead and dive into this. We're going to have a 0 tangent slope really wherever we have these kind of maximum or minimum values on our function. And I think we can see 3. So 1 down here, 1 up here, and 1 down here at 3. So it looks like there's kind of 3 points, and I'll kind of approximate these just for this example where they are. It looks like one is right around -3. We'll say it's at x equals -3. We'll have another critical point there at the maximum. We'll call that maybe 1/2 right at the top of the graph, x equals 0.5. And then we'll have another one there on the x-axis, happens to drop right on the x-axis, but that's also where we'll have a tangent line slope of 0. That would be at x equals 3. So we have 3 critical points on this graph. There's no point on this graph where the derivative is undefined, so we don't have to worry about that case on this example. So again, these are the points at which f prime of x is equal to 0. Those are our critical points. That would be defined as those 3 values, -3, 0.5, and 3, approximately. Now let's consider where is the function increasing. So increasing, if we want to relate that to our first derivative here, an increasing portion of our function would be an interval on which our first derivative is positive. So another way of saying our function is increasing, or what we'd say f of x is increasing, we could say that f prime of x is greater than 0. So that's another way to describe this characteristic. So let's go ahead and consider where that would occur. I'll use the green color here for increasing. Looks like our function is going to be increasing, again, wherever I'm growing from left to right. As x increases, my y values also increase. That looks like in between these first 2 critical points, between -3 and 1/2. And we'll note these with the x intervals. So from -3 to 0.5, we'll have an increasing portion of our function. And we'll have another one, everything greater than +3. So we'll union that interval with an interval from +3, we'll call up to infinity. Again, this polynomial will kind of increase without bound towards x infinity. So forever on that graph. If I considered a decreasing function, we could say that the decreasing function is characterized where f prime of x is less than 0. That would be a decreasing portion of my function. The slope is negative. So where do we have a negative slope? F prime of x would be decreasing. Let's go ahead and try that out in red. I think those would be those 2 other intervals where we decrease from left to right. Our functional values get smaller as we move from left to right on our inputs. We have 2 intervals there. The first interval we could label as -infinity up to our first critical point at 3, and then union that with the interval from 0.5 all the way to +3. So it looks like the whole domain of our graph here is broken off into either an increasing or decreasing interval for this function. One point I do want to make about these increasing and decreasing intervals is notice that I'm using our parentheses or our open intervals. So each of these intervals here are open because at the singular point, specifically at our critical points, 3, 0.5, and -3, and I need to add a negative sign here, each of those critical points, at the singular point there, we're neither going to be decreasing or increasing. We're actually constant at a single point. So whenever we're listing increasing and decreasing intervals, we always want to use open interval points here. So those parentheses are going to be really important for our notation. Let's go ahead and dive into the next collection of questions. These are going to be referring to the second derivative. So part D asks us to identify what are the x values of the inflection points of f of x. So this again is going to be a little bit of approximation based on the graph, but hopefully we get an idea of where inflection points will be and what they look like. So an inflection point, just again by definition, we could go up to our definition from earlier, is saying an inflection point will happen where f double prime of x is equal to 0. So this is where f double prime is equal to 0. In other words, we want to kind of show where our rate of change is maximized or minimized. So this is going to be where our derivative or rate of change is maximized or minimized or optimized. So let's go ahead and dive into the graph and see where we would say that those are maximized or minimized, or in other words, where we change concavity. This is another way to think. We change concavity. Right here. So let's go ahead and grab those inflection points. So if I look into this graph, I'm going to kind of start with kind of this concave up structure, kind of bending up like a U. This first kind of interval, we have concave up structure all the way up until some point kind of right in the middle of this line. I'll kind of list that in blue, and maybe about negative 1.5 there. And again, I'm just going to approximate that point right now. The point doesn't necessarily matter specifically what it is, but we can kind of see that there's a change in curvature where I go from this concave up structure, kind of like a U, towards a concave down structure in the middle of our graph. And again, if we go to the other part, we look like we're concaved up again on the right side of this graph, where we go up from positive 3. So again, maybe from about maybe 1.5 or so, we kind of change our curvature again, and then we start swooping kind of in an upward direction and kind of cup up instead of down. So I'm going to just choose there approximately maybe negative 1.5 and 1.5 for those inflection points, we'll call those. So let's go ahead and just jot those down as possible inflection points. X is equal to 1.5 and negative 1.5. I think those would be good options there. Now, we've already kind of listed out at least kind of where we're concave up, CU, and concave down. It looks like we have two intervals where we consider this as a concave up structure, and that would be from negative infinity up to our inflection point. That would be negative 1.5. And then we'll union that with our second interval. That's our second inflection point, 1.5, all the way to positive infinity. We'll assume that the trend goes on in that direction. So we'll say that's from positive 1.5 to infinity, would be concave up. And then that concave down structure in the middle of the graph, we can answer part F with. Where's that function concave down? Well, it would be in between those two inflection points from negative 1.5 all the way to 1.5. So if that's where we've defined our inflection point, that's where we're going to be concave down. Couple items to kind of finish up this is considering combinations of the first and second derivative. So part G, we're asked to just choose an x value. Again, there could be multiple solutions to this. choose an x value where the derivative f prime is greater than 0 and where f double prime is less than 0. So I'm going to use maybe a specific color to mark out this. I'll do it in purple. So I want really a portion of my function where the slope here, or my rate of change, is positive. So slope is positive. So I'm increasing. And then if f double prime is less than 0, that means I'm concave down. So increasing and concave down, if I go to my graph, concave down and increasing both, looks like maybe as a singular point here, we could choose maybe -1. Up here at -1, we would be increasing in slope, and we're going to be concave down in concavity. So I'll choose x equals -1 here as one of the choices. That'll work for a solution there. Just as an example. Let's go ahead and take a look at the second one. The second one tells us we want to have a function or a point on the function that has a positive first derivative again. So that's again increasing. But this time we would like a positive second derivative, which is concave up. So concave up and increasing. Let's look at our graph. Concave up and increasing. Couple options we could go with here. Over here at 4, x equals 4. If we fill in that point right there, that would be one example. Anything on that interval of points where we're concave up and increasing would work. I'll just use x equals 4 as one example. And we can certainly go through the graph and do all the combinations here. Just for time, let's go ahead and go down to our next page where we'll highlight kind of a similar looking graph and where we'd have all these combinations. So I have red, blue, green, and purple portions of our graph here. This is another polynomial graph. All the red portions of our function would be listing where we are decreasing and at an increasing rate. So we'd be decreasing at an increasing rate. That would mean that we have a negative first derivative, positive second derivative. So if our rate of change is itself increasing, that would be the concavity being concave up or positive. The blue sections tell us that we are increasing at an increasing rate. That would mean that we are both increasing and concave up. That's f double prime is greater than 0 and f prime is greater than 0. The green portion tells us that f of x is increasing, we're increasing, and we're increasing at a decreasing rate, meaning that as we go from left to right, the actual slope is decreasing, but it's still positive over that span. So as we go from left to right, the slope is starting to kind of flatten out, going from left to right there. So we'd say those values would flatten out there. And then the last portion would be the purple portion of this graph. That would tell us that we are our function is decreasing at a decreasing rate. And so that's meaning that we are decreasing in slope. F prime is less than 0, and f double prime is also less than 0. So concave down and decreasing. So we can also consider what we'll call the second derivative test. So let's go ahead and just talk about what that is and then apply it with a quick example. So the second derivative test tells us for each critical point C, where f prime of C is equal to 0, we can find f double prime of C and test whether or not we have a maximum, minimum, or neither. So if f double prime of C, the critical point, is less than 0, then f is concave down, and x equals C, that critical point, is going to be a local maximum. So in other words, if we have a critical point where we are concave down, so a concave down region, the critical point where our derivative is equal to 0, again, will be a maximum. So that's our part A right there. Part B, if that critical point, if we evaluate at f double prime of C and that is greater than 0, that means we're going to be concave up, and x equals C, this is going to be a local minimum value. So at x equals C. So if we consider that case, part B, we would see if we're concave down the critical point that we construct, again, here is going to be a minimum value. The last case is where our f double prime of C, the critical point, is equal to 0. If this is the case, then f may have a local max, it could have a local min, or it could have neither. So that's going to be an inconclusive case there. So we'll have to do further investigation, maybe with a graph of the function, or just go back to the first derivative function and consider what's happening. So let's go ahead and jump into an example where we have critical points and we might need to test using this second derivative test. So let's go ahead and consider the function f of x, where x equals -2, 0, and 2 are all critical points of the function. And we want to determine if each point is a local max, a local minimum, or neither. So let's go ahead and try these out. Again, to test these with the second derivative test, I need to find a second derivative of my function. So let's go ahead and list out the first derivative. We would say the first derivative is going to be 4x cubed minus 16x. The second derivative, we'll just do a derivative of f prime. F double prime is going to be 12x squared minus 16. And now we're going to go ahead and test each of these critical points, whether or not they are maximum, minimum, or neither. So each of these values, again, these are our critical points. We could call those little c's, critical points. Let's go ahead and test -2 first, 0, and then 2. So f double prime of -2, if we evaluate the function at that first critical point, we're really only concerned here with the sign of this critical point. So if I go ahead and evaluate, and you can do this as well, 12 times -2 squared, which would be 4, we have 48 with that product. We'll have a positive 4 times 12 minus 16, which gives us a grand total here of 32. In other words, this is greater than 0. And so since this is greater than 0 or positive, we would say this is concave up right now at x equals -2. Therefore, -2 itself is going to be a local maximum. Another thing that we could be concerned with is, where is this point actually found? And to do that, we might want to find the functional value f of -2. Where is this location of this maximum? If we do that, you'll find evaluating that, you can take a moment to do so, and you'll find that this is going to add up to -18. So it'll be at the point -2, comma, -18 for our local maximum. So -2, -18. Let's go ahead and test the second one, f double prime of 0. F double prime of 0, we'll go ahead and do that. Looks like f double prime of 0 is just going to be equal to, this first term will be 0 itself, minus 16, which would be just minus 16. Which again is going to be negative, meaning that at this point in time we are concave down. Therefore, at x equals 0, we're going to have a local maximum. And I listed the other one wrong. So if we are positive here, that again would be local minimum for that first one. Excuse me. Local minimum. So local minimum again, because if we have a positive second derivative, again, that would notate that we have concave up structure, minimum value. There we go. And then our second value here, concave down, will give us a local maximum. So let's go ahead and write that through. So this would be a local maximum at x equals 0. And again, to find that point, f of 0, go back to your original function. If you look at that original function, evaluate at 0, it looks like you're going to be finding that at just -2. F of 0 is going to be -2. So at the point 0, comma, -2, we're going to have that local maximum. And we're running out of space here, but I think we can kind of put this in. The last portion that we want to test is at f double prime of +2. So f double prime of +2. And I think you'll find that this gives us the same result as -2, since this first value is squared. So this will give the same result as f double prime of -2, which is, again, 32. So since that is positive, x equals 2 here will give us a local minimum again. Since this is a positive value, it's greater than 0. And the last but not least, we can go ahead and find that original functional value. And at f of 2, we will get actually the same functional value as the original. So f of 2 is going to have that same functional value of -18. So we'll have another minimum value at 2, comma, -18. That'll be those 3 critical points. 2 will be minimums, and 1 will be a maximum. One thing I do want to touch on next is the idea of higher order derivatives, and we'll take a look at doing a fourth derivative. And for this question, if we wanted to take a fourth derivative of a third degree polynomial, let's go ahead and just list these out. We'll have first the y prime is the first derivative. We could say that that's going to be negative 6x to the squared power, or the second power, plus 14x minus 6. So that would give me a first derivative. A second derivative we could call, again, y double prime. That would be in the notation for the second derivative. We could say that's negative 12x plus 14. A third derivative we could call y triple prime. And it's kind of getting busy there in the kind of the upper portion with 3 tick marks there, or primes. But this would be notated just like that with negative 12 as the derivative. Once we get to kind of higher orders after this, we usually just use the notation of maybe y4. And again, we put that in a parenthesis there, y4, notating the fourth derivative. We don't want to confuse it with an exponent, so make sure you put a parenthesis around that so it doesn't get confused for a power. And if we take a derivative of a negative 12 constant, this is certainly going to just go down to 0. So a fourth derivative of a third degree polynomial, this is a third degree, third degree polynomial goes down to 0. So one conclusion that we could make, maybe with this next question, is what could we say about the 12th derivative of a 11th degree polynomial? Well, probably just exactly what you think here. We could say that this 12th degree polynomial, or 11th degree polynomial, would become 0 after taking its 12th derivative. So another notation we use is that d notation. So d12y and dx12, that would be the 12th derivative in d notation. We'd say that's going to be equal to 0. Or again, if we wanted to use the y notation, y parenthesis 12, that would be also a 12th derivative. Again, for this case, that would be 0. So just some logic there to kind of help us get through those higher order derivatives and how those work for polynomial functions. This is a little table that you guys can take a look at to consider the relationship between the first and the second derivative. So in the purple on the left side, we know that if our function is constant, that would mean that the derivative is 0, or we would have a critical point. When the function is increasing, our derivative is positive, and when our function is decreasing, our derivative here should be negative. And the relationship kind of follows along the same lines with the first and second derivative relationship. So if our first derivative is constant, that would mean that we will have an inflection point. So it's neither increasing nor decreasing at the inflection point. If our first derivative is increasing, that means really the acceleration. We have acceleration is positive. We would say that the second derivative is positive, or concave up. And where the first derivative is decreasing, we would say that the second derivative would be, in other words, negative, concave down. So first derivative decreasing means concave down. First derivative increasing means we're concave up on that region. So just to pique our interest into what we'll do next in terms of finding critical points and concave and concave down regions, we're going to just do our kind of first example in this with an assist from a graph. So if I looked at this function and I wanted to find the intervals where this g of x function is going to be increasing, decreasing, and concave up and concave down, I can already get kind of a good idea where these things are going to happen based on this graph. But I'd like to be a little bit more specific and use calculus to be exact with where these points occur. So we already can kind of consider we're going to have a critical point or a maximum up at the top there. And maybe, if I were to guess, maybe around x equals 0, and then an inflection point maybe in between those two values somewhere. So let's go ahead and go through the process of how we would actually find where we're going to be increasing and decreasing first. So we'll take a look at part A and part B together right away. So to tackle A and B, I want to first find the critical points of this graph. Where are these actually located? I think they're located here, but let's be specific about where they fall. So I'm going to find in this case, a g prime of x function. And I'm going to see where my derivative here is equal to 0. So let's take g prime first. This would be, in this case, 5x to the 4th, taking a derivative of our original given to us. And then we'll have plus, bring down we have 5/3, and then we'll want to bring down our 5 here, our 4, as the power. That would be 20 over 3x to the 3rd. That would be our first derivative. So to find our critical points, I want to go ahead and set this derivative equal to 0. So I'm going to set this derivative equal to 0. And then solve for x in that equation. And again, we're kind of expecting there to be 2 critical points in this graph. So let's see if we can help that, or hopefully infer that with this graph. So let's do a little bit of factoring here. We can say that we can factor a full 5x cubed, I think, out of both of these terms. Let's consider what that would give us: a x in the first term, and then we'll have, looks like a plus 4 over 3 in the second term left over if I factor out a 5 from the numerator and the x cubes. So setting both of these 2 separate pieces together first, we could say that one critical point could be found by setting 5x to the 3rd equal to 0. That's certainly just going to give us 0. And if I set the second factor equal to 0, this one is going to be forced to be negative 4/3. So we have really 2 critical points here where our first derivative is equal to 0. We'd say that's 0 and negative 4 over 3. So let's go ahead and label those on our graph here, and that will help us to consider where our increasing and decreasing intervals are. So that is in fact 0. So those 2 are going to be my specific critical points, meaning we could say with confidence that for this specific function, I'm going to have an increasing interval starting at negative infinity up to my first critical point at negative 4/3. And I'll also be increasing here, looks like, again, with aid from this graph, from 0 to positive infinity. In future lessons, we won't necessarily use that aid of the graph immediately, and so we'll have to figure out how to determine what regions are increasing and decreasing based off of those critical points. The decreasing intervals we could label as well, and we could label these in between these 2 critical points. That'll be 1 interval there, and that'll be the interval from negative 4/3 all the way to 0. Again, with the aid of that graph. Concave up and concave down is the last components that we want to consider. So to do that, we want to consider where's the second derivative equal to 0. We'll try to find that inflection point first. Once I find an inflection point, I'll be able to find those intervals. So let's go ahead and take our first derivative and take its derivative to find g double prime. So g double prime of x will have two terms. Looks like we'll have 20 x cubed for the first term. And then if I take the derivative of the second term, that 3 power will bring down and cancel with the 3 that's already there. So we'll end up with a second term of 20 x squared. Again, I want to go ahead and set this second derivative equal to 0. And go ahead and solve for my possible inflection points. So if I set this equal to 0, looks like I can again factor. Here we'll factor out 20 x squared and be left with x and then plus 1. So two possible inflection points that we could bring from this or gather would be, first, x equals 0 is a possibility. And then secondly, x equals -1. Now, again, with the graph as our aid, let's go ahead and take a look at which one of those makes sense. It does make sense here that maybe x equals -1 could be an inflection point where we change concavity. I think that would be appropriate here. But again, here, x equals 0, that doesn't look like necessarily a change in concavity. It does look like a minimum value, but in this case, I think we would have to throw out that as a possibility for our inflection point. I don't think we have 2. I think we're just going to have 1 at x equals -1. So with that, we have an inflection point at x equals -1. So we will have a concave down structure, again with the aid of our graph, from -infinity to -1. And that's a concave up first. Let's do the concave up would be from -1 to infinity. And then concave down a second here, that'll be from -infinity to -1. So again, this is just kind of hopefully giving us a preview of what we're going to consider with these critical points and testing whether we have a concave up or concave down region. Look forward to seeing you in the next video where we look at optimization a little bit closer and consider a first derivative test as well. Thanks for watching.